questions 21 through 25 on the 2020 Grade 10 Cayley Math Contest. How many points xy with x and y both integers are on the line with equation y equals 4x plus 3 and inside the region bounded by x equals 25, x equals 75, y equals 120, y equals 250? So we have a line somewhere, and we've got to basically find integer solutions. So let's draw this like entirely based on the boundaries that they've given me. So we got 25 and 75, so approximately here and here. And this won't be drawn to scale, but 120 and 250. So approximately something like that, where this is 25, this is 75, this is 120, and this is 250. And then now let's plot this y equals 4x plus 3. When x is 25, we're going to have a 103, so approximately here. And when x is 75, we're going to have 303, so somewhere here. And then let's connect those two lines to get an idea of what this will look like, so something like this. So now the equation has to be looked at in terms of these boundaries. So let's just make a little table for ourselves, x and y, and off we go. So they want it inside this region, so we obviously have to go above 25, so let's go to 26. When x is 26, when you plug it into that equation, we get 107. When x is 27, we get 111. When x is 28, we get 115, and so on, right? 29 will give you 119. So far, my x is within that boundary, and my y's are within that boundary. Well, not yet, right? Because 119 is not 120. I got to keep going. 30 gives me 123. Now I can say I am within my boundary for both x and y. And then we just keep going like this, dot, dot, dot. And then eventually you can kind of figure out, when will I get beyond that boundary? And you go beyond that boundary when y is above 250, right? 250 or equal to 250. So that basically means that 250 is going to be equal to 4x plus 3. So that means 247 is equal to 4x. So x is equal to 61.75. So that means that once you get above that, you're going to get beyond the boundary. So if it's 62, if we plug it in, it becomes 251, and indeed we are above that boundary. So 61 is 247, and we're still within our range. So that means these values are the ones that are within the range, and we have to just count them up. So it's all the integers from 30 to 61, so that's 61 minus 29, and that is 32. So number 21, the answer is D. In the diagram, points S and T are on sides QR and PQ respectively. Triangle PQR, so that PS is perpendicular to QR and RT is perpendicular to PQ. PT is 1, TQ is 4, and QS is 3. What is the length of SR? Here's that diagram, and let's label what we are given in the question. That's 1, this is 4, and this is 3. SR is what I have to figure out, so I'll just call that X. Well, this I can easily figure out in terms of Pythagoras. So PS squared plus 3 squared is equal to 5 squared. So solving for that, you get PS is equal to 4, if we need it at all. Now I see a similar triangle situation. If I call this theta, and this triangle right here, since that's 90, this angle will be 90 minus theta. And then in a very similar way, if you look at this triangle, this is 90 degrees, so this will be 90 minus theta, that angle in there. So I'll just put that in there, 90 minus theta. So that basically means that triangle TQR is similar to triangle PQS. So from that, we can deduce that the ratio of the sides will be the same. So TQ over QR, matching the angles, will be equal to QS over PQ. TQ is 4, QR is 3 plus X. QS is 3, and PQ is 1 plus 4, which is 5. So cross multiplying to get 20 is equal to 9 plus 3X. So that means 11 is equal to 3X, and therefore X is equal to 11 over 3. Number 22, the answer is B. Ricardo wants to arrange 3 1s, 3 2s, 2 3s, and 1 4 to form a 9-digit positive integer with the properties that when reading from left to right, there is at least 1 1 before the first 2, and at least 1 2 before the first 3, and at least 1 3 before the 4. And no digit 2 can be next to another 2. For example, the integer 1 2 1, 3 2 1, 2 3 4 satisfies these properties. In total, how many such 9-digit positive integers can Ricardo make? We have 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. And they are 1, 1, 1, 2, 2, 2, 3, 3, and a 4. So we have to place them according to these rules. Okay? Well, based on these rules, the first number must be a 1. There's no other way that you can do this. You can't put the 2 first because the 1 has to appear first. Okay, now after that, we've got a few choices. The next number can be a 2, or you can have 1, 1, and then 2. That's perfectly valid. Or you can have all 3 1s, and then the 2. So these are essentially our 3 cases. And then for each of these cases, we of course have to find a number of different ways to fill out the rest of the spaces, because the answer choices are much greater than 3. Okay. So let's begin, and I think I will start with the last one first. So that's going to be the 1, 1, 1, and then a 2, and then after that I have 1, 2, 3, 4, 5. 5. Now I've already used 3 1s and a 2, so the numbers I have remaining are 2, 2, 3, 3, and 4. These 5 have to go in these 5 slots. And the general rule in this question is that you can't put two 2s next to each other. So the 2 can't go here, for example. So if I call this 1, 2, 3, 4, 5 in terms of its positions, this is position number 1, position number 2, like that. Or if the numbers are too confusing, you can use letters. That might be a little bit less complicated or less confusing. Then the 2's have to be separated by at least 1. So the 2's can be, for example, in the positions B and D, B and E, or C and E, right? And in that case, we have to now place the other 3 numbers, and the other 3 numbers can be placed as following. It can be 3, 3, 4, or 3, 4, 3. Similarly, this can be 3, 3, 4, or 3, 4, 3. And then same thing, 3, 3, 4, or 3, 4, 3. So basically, if B and D were the places where the 2's were being placed, it would be 3, 3, 4, like that, and then 3, 4, 3, like that. The 4 can't go in slot A because they have to put at least 1 3 before it. And very similarly, the other ones are very the same, but the choices for the 2's are different. It's B and E, so the 2's are here, and the same thing, 3, 3, 4, or 3, 4, 3, like that. And the last one was C and E, so the 2's go there, and then again 3, 3, 4, or 3, 4, 3, and then the 2's like that. So as you can see, that's 1, 2, 3, 4, 5, 6. So 6 ways of making that. Now I wanted to walk you through that instead of just saying, well, this is how you do it, because the same principle applies to these and these 2 cases, but there's going to be a lot more cases. All right, now we've done that one. Let's move to the next one. The next one is where you have the 1, 1, 2 situation. So 1, 1, 2. And then we have 1, 2, 3, 4, 5, 6 numbers. We've already placed 1, 2, and 2 1s. So of these numbers, this one and this one are gone, and so is that one. So we have 6 spots and 6 numbers. So just as before, we have to figure out where to place the 2's. Okay, so I can't put a 2 here, and in the very same way, let's label them A, B, C, D, E, F. The spots for the 2's, it looks like I can put B and D, B and E, B and F, or C and E, C and F, or D and F. So these 6 places is where I can put the 2 2's. So that takes care of these guys. Now the remaining 4, right? If I choose B and D, there's going to be 4 left. 1, 2, 3, 4. Those remaining 4 slots, I have to place the 1, 3, 3, and 4. 1, 3, 3, and 4. Those are the remaining. Now I have 4 slots remaining. Once I place those 2 2's, let's say I chose B and D, then I would have A, C, E, F, right? And I have to place these 4 numbers in A, C, E, F. So I have to figure out how many combinations are possible. And let's see here. We got 4 times 3 times 2 times 1. And that gives me 24. But there's 2 3's, so I got to divide by 2. Because you get an overcount here because of the 2 3's. Because 3 3 is the same as 3 3, if you know what I mean. If the numbers were different, like 3 and 7, then 7 and 3 it would be different than 7 and 3. So that's why you get an overcount. So there's 12. But here's the thing. Some of these 12 will be invalid. They would be invalid, for example, you cannot put the 4 first. So something like 4, 3, 1, 3. Or 4, 3, 3, 1. Or 4, 1, 1, or 1, 3, 3. Those are invalid. And also you can't put a 1 and then the 4 and then put the 2 3's because the first 3 has to appear before the 4. So of the 12, these 4 are invalid. So from the 12 you minus those 4 and that gives you 8. So for the first part of this placement, which were the 2's, I have 6, and then for the remaining numbers I have 8, so I have to multiply those together to get the total combinations, and that's 48. So 48 is what goes here. Alright, so now we are down to the last one, which is a 1 and then a 2, and then we have to figure out what to do with the rest. So I have a 1 and then a 2, and then I would have 1, 2, 3, 4, 5, 6, 7. The numbers are 1, 1, 1, 2, 2, 2, 3, 3, and 4. I have already used 1, 1, and 1, 2. So I've got 7 numbers and 7 slots. So I got to figure out how to do this now. Very similar. I have to first figure out where to place the 2's. And if I label this A, B, C, D, E, F, G, like that, I can figure this out. 2 can't go there because that would make 2 2's together. So it looks like B and D, B and E, B and F, B and G. C and E, C and F, C and G. D and F, D and G, and then finally E and G. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 ways to place the 2's. Okay, so let's just say I put B and D. So that means I've got 5 left in this scenario: A, C, E, F, and G. The 2 2's have been placed, so now I have to place in these 5 the following numbers: 1, 1, 3, 3, and 4. Okay, so I have to first figure out where I'm going to place the 2 1's. So from these 1, 2, 3, 4, 5 slots, I'm going to choose 2 slots for the 1's. So 5 choose 2, that's 10. So that takes care of these guys. And then the remaining 3 slots, I have to arrange those 3 numbers. So it shouldn't be that hard. There's only a few possibilities, either 3, 3, 4, 3, 4, 3, or 4, 3, 3. of these, this one is invalid because the 4 cannot become before the 3. There has to be at least one 3 before the 4. So just this one, and that gives me 2 ways of placing the last 3. So I've got this 10, and this 2. I've got to multiply them. 10 times 10 times 2, and that is 200. So this final scenario is 200. So that means this is 200 here. And then now I just have to add up these 3. 200 plus 48 plus 6 is 254. And therefore, number 23, the answer is C. A cube with vertices F, G, H, J, K, L, M, N has edge length 200. Point P is on H. G as shown the shortest distance from G to a point inside triangle P. FM is at 100. Which of the following is closest to the length of HP? Let's start off with a little bit of labeling. P to G is what I have to figure out because that will allow me to eventually figure out HP. So I'm going to let PG be X. And therefore HP, which is what I have to figure out at the end, will be 200 minus X since the edge length is 200. And then now I'm going to try to figure out some lengths. And some of these are going to be in terms of X since PG is being called X. The first one, not in any particular order, will be PM. And I will use this Pythagorean relationship here since that is a right angle. So PM squared is equal to PG squared plus GM squared. So PM squared is basically X squared plus 200 squared since the edge length is 200. And in a very similar way, we will figure out PF using that triangle. PF squared is also equal to X squared plus 200 squared. And then finally, I'll figure out FM. FM using that triangle right here, where this is a right angle. That squared is equal to 200 squared plus 200 squared. Okay, so those tell me that this is an isosceles triangle. It doesn't appear that obvious when you see it on the diagram because it's on a slant. But once you figure out the values, you see 2 of those values are the same. So I'm going to draw that isosceles triangle. So something like this, where this is F, and this is M, and this is P. And then FP, or PF, is X squared plus 200 squared under the square root sign. And then same with PM, it's also X squared plus 200 squared under the square root sign. So this is indeed an isosceles triangle. And then FM is 2 times 200 squared under the square root sign. And if we do that, that's just going to be 200 times root 2. So we might as well just write it as 200 times root 2. Okay, so now I have to turn my attention to this part of the question stem. The shortest distance from point G to a point inside triangle PFM is 100. That basically means that if you take the shortest distance, it's basically going to hit at a perpendicular to that side. And then that will form these right triangles with the other sides. And as before, we can make relationships. So that means since this is a right angle, that, and I'll call that point right here that it touches A. Obviously, I have to give it a name. So that means that AG squared plus PA squared will be equal to PG squared. And very similarly, AG squared plus AF squared will be equal to FG squared. And also very similarly, AG squared plus AM squared will be gm squared. So AG, they have told me, is 100. Basically, the distance, shortest distance from G to that triangle. So these three equations basically give me the following result. 100 squared plus PA squared is equal to, well, PG is x squared. So that means PA squared is equal to x squared minus 100 squared. And then this guy right here, it will give me AG squared, which is 100, plus AF squared is equal to FG squared. And FG is this, it's just the side, so 200 squared. So we have AF squared is equal to 200 squared minus 100 squared. So that's 40,000 minus 10,000, so 30,000 AF squared. And therefore AF is going to be the square root of that, which would be 100 root 3. And very similarly, AM is going to be the exact same thing. It's the exact same math, so I'll just put AM is equal to that as well. Okay, so now that we've got that, we can go back to our isosceles triangle and label all this. And it is going to be straight down like this. A is going to be some point along that line. I'm not entirely sure where, but somewhere. And then we can connect two lines to show FA and AM like that. And again, since we calculated AM is equal to AF, these are also equal, and they're both equal to 100 root 3. So you can just put that in there. 100 root 3, both of them. Now, since this is an isosceles triangle, this line basically cuts that base in half. So if I call this D, FD will basically be half of that. So it'll be 100 root 2. And this will be 100 root 2. And PA is x squared minus 100 squared under the square root sign. So this is PA. So I'll just draw a little line there. It's x squared minus 100 squared under the square root sign. Now if I can figure this out, it will be very helpful, and I definitely can. I can just use Pythagoras to figure out AD. AD squared plus FD squared, which would be 100 root 2 squared, is equal to the hypotenuse, which is FA, which is 100 root 3 squared. So that means AD squared is equal to, that's going to be 10,000 times 3, so 30,000, and then minus 100 root 2 squared, 2 times 10,000, so 20,000. So that's 10,000, and the square root of that would just be 100. So AD is just 100, so that works out very nicely. So this guy AD is 100. Okay, I think I'm ready to solve. And it's going to be not extremely messy, but a little bit of work involved, using the Pythagorean theorem once again. So we have FD squared plus PD squared is equal to FP squared. Okay, FD squared, that's 100 root 2 all squared, so that's an easy one. And then PD squared, there's two components there. The PA, which is x squared minus 100 squared, plus 100, which is the AD, and that's all squared. And then that's equal to FP squared, and FP squared is x squared plus 200 squared. When you square it, the radical sign disappears. Okay, so that's really good. Okay, so I am going to expand this out. So that is going to be x squared minus 100 squared plus 200 times the square root of x squared minus 100 squared plus 100 squared. And if I put everything on the other side, it'll be x squared plus 200 squared minus 100 root 2 all squared. So this x squared is on both sides, so that can go. This minus 100 squared cancels with that plus 100 squared, and all I'm left with is the remaining. So I will just write what's left. Let's move this up a bit. I can do the math here. This is going to be 40,000, and that's 10,000 times 2, so 20,000. So that's 20,000 when I do that subtraction, and that's 200, and that's x squared minus 100 squared. Divide through by 200, and that's going to be 20,000 divided by 200, which is just 100. Okay, great. And then square both sides, and I get x squared minus 100 squared. The radical disappears. This becomes 10,000. And then x squared therefore becomes 10,000 plus 10,000. So that means x squared is 20,000, and therefore x is the square root of 20,000. And that is approximately 141. And in the end, I wanted to figure out HP, which is 200 minus x. Okay. Well, x is the square root of 20,000, which is approximately 141.42. So if I do 200 minus x, which is HP, 200 minus x, that is going to be equal to approximately 58.57. 58.6, let's say. And therefore, that is closest to choice D, 59, number 24. How many positive integers n less than 20,000 have the properties that 2n has 64 positive divisors, including 1 and n, and 5n has 60 positive divisors, including 1 and n? Let's start with a primer to explain this. Let's say I gave you some number n, and I said, how many divisors does it have? What is the method? Especially when the number is very large. So let's say it's 17,640. It would take an awfully long time to list all the divisors. Well, there's a system. The first thing you do is break it up into its prime factors. In this case, it would be 2 to the power of 3, 3 to the power of 2, 5 to the power of 1, and 7 to the power of 2. To get the number of divisors, you would do the following. You would take this exponent, add 1. Then take this exponent, add 1. And then you would take this exponent and add 1. And finally this exponent and add 1. So this would be the number of divisors. You would multiply them all together. So 4 times 3 times 2 times 3. And that's 12 times 6, which is 72. So that means that this number has 72 divisors. And that is the system we will use throughout this question. So now we are given an n, and we are not told, obviously, the number. The only thing we're told is that it's less than 20,000. So I don't know what its prime factorization is. It could have a 2 to the power of something. It could have a 5 to the power of something. Because this will have a 2 and this will have a 5. So I want to include the 2 and the 5 there, but the rest of the primes, I don't know. So I'll just call them P1, P2, ... And then they will also have exponents, so C and D. Now 2n, therefore if you're adding a 2, multiplying by 2, it would basically make this 2a plus 1. And the rest would be the same. P1, C, P2, D, ... And then 5n, it would basically make it 2 to the power of a, 5 to the power of b plus 1, and then P1, P2, and so on. Now our task is to figure out some 2n that has 64 divisors and some 5n that has 60 divisors. Okay? So where do we begin? And this is the challenging part of the question. You have to sort of do a little bit of brainstorming here. Okay? So what I'm going to do is start somewhere. So let's start with just 1 prime. if I have 2 to the power of A, 5 to the power of B, and some prime to the power of C, then that means 2n would be 2 to the power of A plus 1, 5 to the power of B, P1 to the power of C. 5n would be 2 to the power of A, 5 to the power of B plus 1, P to the power of C. Now, for 2n, using our system, the number of divisors would be as follows. It would be A plus 1, B plus 1, C plus 1. And that has to equal 64. For this one, the number of divisors would be A plus 1 times B plus 1 times C plus 1. And that has to equal 60. Now you have to do a little bit of trial and error and try to figure out, can we make this work? And you can. For example, if this is 4, 4, and 4, it would become 64. And therefore that would make this 4, 5, and 3. And that would be 60. 4 times 4 times 4 is 64. 3 times 5 times 4 is 60. So that basically means that A is equal to 2, B is equal to 3, and C is equal to 3. So my n is 2 to the power of 2, 5 to the power of 3, and some prime factor to the power of 3. And we are told that n has to be less than 20,000. Okay, let's see what I can get. So that means P1 to the power of 3 is less than 20,000 divided by 2 to the power of 2 times 5 to the power of 3. That means P to the power of 3 is less than, that works out to be 40. So that basically means that if you take the cube root, P1 is less than 3.41. And the only prime number less than that is P equals to 3. So we got our first n. It's 2 to the power of 2 times 5 to the power of 3 times 3 to the power of 3. And that number is 13500. And that is indeed less than 20,000. So we got 1. But the answer choices, there is no 1. They're all bigger than 1. So we've got to find a few more. Okay. So I had initially started with 1 prime number. Let's go to the next logical choice, which is 2 prime numbers. So now my n would be of the form 2 to the power of A, 5 to the power of B, and then the first prime to some exponent times the second prime to some exponent. And therefore 2n would be 2 to the power of A plus 1 times 5 to the power of B, B1 to the C, P2 to the D. 5n would be equal to 2 to the power of A, 5 to the power of B plus 1, P to the power of C, P2 to the power of D. Now let's talk about the divisors, number of divisors. For each of these, we have to look at the same system. So it would be A plus 1 times B plus 1 times C plus 1 times D plus 1. And that has to equal 64. And then for the next one, 5n, it would be A plus 1 times B plus 1 times C plus 1 times D plus 1. And that has to equal 60. And again, you have to use some brainstorming now, plug in some numbers, see what we get. And if I look at this, basically everything here has to be a multiple of 2, right? Because that's 2 to the power of 6. So I can't have any 3s or 5s. So I'm going to say, let's say make this 2, 2, 4, and 4. That will work. Therefore, this is also 2 and 2 since those are exactly the same. This is 1 greater, so that will be 5. This is 1 less, this is 3. 4 times 4 times 2 times 2 is indeed 64. 3 times 5 times 2 times 2 is indeed 60. So that took some trial and error. But when you do it like this, it works. So that means A is equal to 2, B is equal to 3, C is 1, and D is 1. So that means my n is equal to 2 to the power of 2, 5 to the power of 3, P1 to the power of 1, and P2 to the power of 1, and that's got to be less than 20,000. So that means P1 times P2 is less than or equal to 20,000 divided by that 2 to the power of 2, 5 to the power of 3. So P1 times P2 is less than or equal to 40. So that means I've got to have two numbers that when multiplied together are less than 40, two prime numbers. Well, our prime numbers, not including 2 and 5, because those have already been used, are 3, 7, 11, 13, 17, and so on, right? Let's see what we get. What combinations can I put here to make it less than 40? Well, I can use 3 and 7, that's 21. 3 and 11, that's 33. 3 and 13, that's 39. And I think that's it. After that, basically, we would run out of ways of making two prime numbers multiplied together to be less than 40. So now I've got a few more n's. The first n would be 2 to the power 2, 5 to the power 3, 3 times 7. The next one, 2 to the power 2, 5 to the power 3, 3 times 11. The next one, 2 to the power 2, 5 to the power 3, 3 times 13. And let's get the numerical values for each of these. They are 10,500, 16,500, 19500. So there we go. I got 1, 2, 3 additional n's, and then we add it to that, so it gives me 4 possible values of n. 4 values of n is the answer, so therefore this challenging question, number 25, the answer is A.